What if numbers -1000 and -10 are almost treated exactly the same? They both become almost 0. And the numbers 10 and 1000 both become almost 1. The only values that really matter are the ones near the middle. That's the magic of the sigmoid activation function. Inside every neuron, we first calculate a value called z. This value can be anything from a very large negative number to a very large positive number. But in many tasks, especially binary classification, we don't want any random number. We want a probability between 0 and 1. That's exactly what sigmoid gives us. Meet the sigmoid curve. It's a smooth S-shaped curve that transforms any input into a value between 0 and 1. As z becomes very negative, the output gets closer and closer to 0. As z becomes very positive, the output gets closer and closer to 1. And when z is exactly 0, the output is exactly 0.5. Here's how to read the curve. Values near 0 mean the neuron is mostly off. Values around 0.5 mean the neuron is uncertain. Values close to 1 mean the neuron is strongly on. Notice that the curve is steep in the middle, where small changes in z make a big difference. Near the edges, the curve becomes almost flat, so even large changes in z barely affect the output. Let's compute a few examples. If z equals -5, the output is about 0.007. At -2, it's about 0.12. At -1, it's 0.27. At 0, it's exactly 0.5. At 1, it's 0.73. At 2, it's 0.88. And at 5, it's already about 0.993. You can see how the outputs quickly move toward 0 or 1. Now for the math. The sigmoid function is 1 divided by 1 plus e raised to the power of -z. Here, e is a mathematical constant. -z controls how quickly the output changes, and sigma of z is the final probability. An interesting bonus fact is that its derivative can be written using the sigmoid output itself, making it mathematically elegant and easy to compute. So, what are the advantages and disadvantages? Sigmoid produces outputs that look like probabilities, it's smooth, and it's easy to interpret. But it also has important drawbacks. The gradients become extremely small for very large positive or negative inputs, making deep networks harder to train. Its outputs are not zero-centered, and computing the exponential function is slower than simpler activations like ReLU. Let's recap. Sigmoid converts any number into a probability between 0 and 1. The middle of the curve is where learning happens the fastest. Extreme inputs are pushed close to 0 or 1. It's great for binary classification, but its vanishing gradient problem makes it less suitable for deep hidden layers. Follow the Daily Deploy for more AI and deep learning concepts explained visually.